Welcome all of you for this class on specific energy, specific force and critical flow, which is a part of steady flow in a river flow systems, which we try to understand it, how energy dissipates, how the mass conservation equation we can use it, and the momentum, linear momentum equations for solving the river flow. And mostly we targeting now the steady flow analysis using specific energy concept. That's what we discussed in the last class, and today we are going to discuss about specific force and the critical flow. That's quite interesting to know it, how the flow happens in a river. Considering that, if you look at the slides what we are following, more details of Anit Chaudhary books, okay, for the steady flow, as well as we are following river mechanics books by P.Y. Julians. These two books we have been following for steady flow, which is necessary for to analyze it, how the flow behaviors. Is it a subcritical, supercritical, critical, what the conditions are there, and that's things we are going to discuss more as in the last class what I discussed it. Beyond that, today we will discuss it. Let's go back to the same slide what I discussed in the last class. Is that if you look at in a rivers where you have the hilly rivers and you have the stones or the boulders positions like this. So in that case you can, as we discussed, there will be stagnation points, there will be the critical depth, and there will be the hydraulic jump formations. There will be hydraulic jump formations, and there will be the flow. Because of this resistance, we can have the turbulent structures, the energy dissipations. That structures will be there, which we can consider it how the bed roughness is playing the roles for creating the turbulent structure as well as the energy dissipations. But more details we can look at now, the critical depth and the hydraulic jumps, which is quite related to each others. Before that, you know it that from the fluid mechanics, the flow Proud numbers is the ratio between inertia force by the gravity force. If I considering a channels having the flow depth is h, flow depth is h, and v is the velocity, and the area of the flow is a. If that is the conditions I have, I can find out the inertia force will be rho a v square. Is a rho into q is a mass flux into v is a momentum flux, which is as equivalent to inertia forces for a flow when you have a h depth is moving with v velocity and area of cross sections a. We can find out the momentum flux will be rho a v squares, which is the inertia force divided by the gravity force. For this case, you will have a rho g a h. Okay, h is the depth, multiplied with area, it's a volume into the density, then you multiply with the acceleration due to the gravity, you get the weight. That's what is the force due to the gravity. If you have these components, if you look at v square by g h, or I can say it v by root g h. Please remember it, it's a ratio between two force components, inertia force and the gravity force component, which as equivalent we are considering it, the fluid mass is moving with uniform velocity v and it has a flow depth h, and you try to find out what is the relationship. So when I talk about the flow Proud numbers is greater than 1 or I am talking about the flow proud numbers is equal to 1. What does it indicates that? That is the conditions where the gravity force is equal to the inertia force. That the conditions it happens it when you have the critical flow or the flow proud numbers is equal to 1. But if you have a flow proud numbers is more than 1, the inertia forces is larger than the gravity forces. The interpretations, if you look at this flow proud number is greater than 1, what it indicates is that the inertia forces is larger than the gravity forces, and that is the conditions when you have super critical flow. Okay, just reverse, when you have a flow probability number lesser than 1, you can interpret it in terms of gravity forces and the inertia forces. Inertia force is nothing else, is a momentum flux, as we consider a control volumes of a smaller control volume which is having a flow depth of h and area of this cross section A, and it's moving with a velocity v. We can very easily you can derive this, the ratio between inertia forces by the gravity forces. That's what is given the definitions about the flow proud numbers. That's what could be discussed in fluid mechanics book, but let me understand it. When you have the open channel flow or the river flow, you can have a stretch where you can have a subcritical flow, and there could be a stretch you can have a supercritical flow. And during this period, the transitions of the supercritical to the subcriticals, like these cases, you will have a hydraulic jump formations. You will have hydraulic jump formations. That's the regions you will have a high dissipated of energy. So use the hydraulic jumps as a design for energy dissipations or creating a turbulent structures for the mixings of the any fluid mixings. We can do it, or fluid and sediment mixings we do it. We try to use a hydraulic jump as a energy dissipators, or we can use a hydraulic jump as a mixing of these the flow systems. That's what we use the hydraulic jump concept. But in case of the rivers, we try to understand it where the hydraulic jumps occurs and what is the amount of energy dissipations because of the hydraulic jump formations. Let's go to the hydraulic jump part, which already we discussed about the specific energy. Let's come back to the hydraulic jump. The hydraulic jumps, it happens when a supercritical flow changes to the subcritical flow. That means very simple way, but if you look at it in terms of flow proud numbers, in the supercritical flow where you have a inertia forces is larger than the gravity force. When that changes is happening as terms of force, that's the mechanisms happens from supercritical to subcritical. That means the supercritical where the velocity is higher, the depth is lesser. Okay, and that is the conditions when it happens there is a formations of hydraulic jumps, like you will have a formations of hydraulic jumps. Okay, so there is the points. What if you look at this, the specific energy curve. Okay, and you can see that if I consider y1, the energy at this point is this, and y2 is energy here. There is a energy losses in these hydraulic jumps, and there will be noise or the sound production by heat energy and turbulence energy. All they work it to dissipated energy in the formations of the hydraulic jump from the supercritical to subcriticals. That's what you know it. Basically, it's we call sequent depth or conjugate depths. Okay, that's the theoretical points. I look at these hydraulic jumps as a part of specific force concept. When you consider a specific force concept, I can use a control volume. I can use a control volumes like this. I can use control volume. So, when I use these control volumes, then we try to look at what is the force is acting on the control surface. In this case, if you look at that, in this surface there is no force is acting on, and at this surface there will be frictional forces, and the frictional forces what is acting in the short reaches we can consider it is a 0 or it is a negligible, it is not that significant. So, if that is the conditions, and here if I consider the pressure distribution is hydrostatic pressure distributions, and it is quite valid. If there is no curvatures of the free surface, we can assume we can use the hydrostatic pressure distributions for this flow. So, we can have a hydrostatic pressure distributions. We can have hydrostatic pressure distributions. So, I know the pressure distributions, I know this, the momentum flux what we are coming it here y1 v1, the y2 v2, I know this velocity, I know the depth, and if I consider unit width, I can find out what is the change of the momentum flux happening in these directions. That should be equal to the net force is acting along these directions for this control volume. So, if you apply that, so what are the forces we have? The momentum flux, the rate of change of momentum flux, and the hydrostatic pressure distribution, because we have neglected the frictional force components and there is no force, significant force will be there, the interface between the water and the air. So, that we can neglect it. So, that way if you look at that, if that is the conditions, we have only the two forces components. That is the concept is called specific force. If you look at that way, as again I can to sketch the control volume and equate the force components. If I look at this is what momentum flux component, this is the component because of hydrostatic pressure distributions at the section A, that what will be equal to the force component per unit weight, force component per unit weight due to the hydrostatic pressure distributions at the two locations and one. That is what the relationship what is gives is a nothing else, it is a linear momentum equations. When apply for these control volumes, we will get it that, and that force component per unit weight, if I define it, that is called as a specific force. That is we call specific force. That means what we are looking at here, we are looking at for these control volumes, we apply where the hydraulic jumps happens it, we apply the control volume, we apply linear momentum equations, and as we consider there is no significant frictional force is acting on this short reach, then we can write the force terms and linear momentum equations in terms of two components. One is the linear momentum flux component per unit weight, pressure force component per unit weight. That is what if I put it, that is what is represent as equivalent the force component at the E1 and 2, that is what we are equating. Is nothing else, is a linear momentum equations applications for this control volume, and per unit weight if you define it, that is what will be defined as a specific force. So, that is what is indicating it, that if I considering a free surface flow where we have the hydraulic jumps, we can easily find there is no significant other forces are there, not there. So, we can use a very simple concept that the specific force at the section 1 and sections 2, that should be equal. That should be equal. That is the specific force will be the same, but there is an energy because this hydraulic jump there is a energy losses, there is in specific energy diagram 1 and 2 will be in the different locations, but in case of the specific force diagrams it will have in the same specific force what is there at the 1, and that is what equal to 2. So, in case of the hydraulic jumps we use the specific force concept, or we use the linear momentum equations to derive, because we know it, there is no significant other forces are there, just we equate it other than the momentum flux and the pressure forces, can equate that forces which is a specific force at section 1 and section 2, if you equate it, and if you use a simple geometric relations for a rectangular channels like area is equal to B into Y, and the centroid or the pressure centers, if I can find out, and if you use these two equations and the continuity equations, and in terms of the upstream flow Proud numbers, we can find a relationship between Y2 and Y1, which is a functions of upstream flow Proud numbers. That is a very simple things, just you use linear momentum equations, mass conservation equations, and the definitions of flow Proud numbers, upstream flow Proud numbers at the sections 1 before the formations of the hydraulic jumps. You can, using that two equations, you can modify it, you can get a relationship between the Y2 and Y1 is a upstream, the before hydraulic jump depth and after hydraulic jumps depth. That is the relationship, we will get it, which is a functions of upstream flow Proud numbers. Upstream flow Proud numbers. They are very simple concepts, only we are using linear momentum equations, mass conservation equations, and the definitions of flow Proud numbers to derive these ones. These very easy things, and always whenever you solve these problems, any flow problems you draw for the steady flow problems, we should draw specific force diagram, also specific energy diagram. So, you can have the two diagrams, one is a specific force diagram, another is specific energy diagram, and then you try to interpret it, that what is happens it pre-hydraulic jumps and post-hydraulic jump, and what could be the, we use a simple tools of linear momentum equations for this control volume and the mass conservation equations. That is what we can derive it. It's we have not used any new things except this basic principle of mass conservations, linear momentum equations, and energy conservations for the control volume. That is what we are doing it for a very simple problems like a flow in open channel where the hydraulic jumps occur. Let us have a very simple problems to solve it. A 4.5 meter wide rectangular channels carrying the discharge is 50 cubic at the depth of 3 meters. There is a step rise, that is a step rise of 0.25 meter. That is, and if it is that is the conditions, determine the flow depth downstream of the bottom steps. Does the water surface rise and fall at the steps? So, if you look at these problems, it is a very easy problems, that there is a rise of the bed, okay, there is a step rise of the bed because of maybe the sedimentations, maybe man-made structures we can have the wear, okay, there is a rise of the bed naturally or man-made. If that is the conditions, we can use the specific energy concept now. We can assume it that energy dissipations are not that significant. So, I can use the specific energy at the two sections, section 1 and sections 2. I can compute this specific energy at the section 1 and the sections 2 the specific energy will be lesser than E1 because of this rise height which is a 0.25 meter, and that's the reason we will get this E2 value. So, as I know the specific energy at the E2 values, and from that substitutions I will get a relationship between Y2 and A2. So, that is the reasons there is 2 unknowns are there, and A2 is a functions of the Y2 because B is known to us. So, if that is the conditions, we can use a heat and trial methods because of this is a quadratic equations levels, this is a cubic equations levels, and we can compute it at the heat and trial methods. It will have these 3 values, one of the things will be negative which we do not consider it, and another is 2.73. We can ask it, why do you consider 2.73 not the 0.49? That is the same concept what I used in earlier in a explanations in the specific energy we have discussed, is that we should try to know it whether the flow is subcritical and supercriticals. If it is flow is a supercriticals, then the water level raise will be there. In case of the subcriticals will be decrease will be there, and this case, as you know the flow upstream flow Proud numbers, you can compute it and you can find out flow is subcriticals. So, that is the reasons the depth what will be the falling of the waters. Okay, that is what will have a falling of waters, that the conditions what we will get it. Just try to solve that. Okay, in numerically it is quite easy. Let us talk about another simple example problems where we are telling it there is a reservoir which is 25 meter wide spillway. This is a spillway. Just look the figures. This is a spillway. In generally, whenever if you look at the rivers, dam projects, you can have the spillway. It is having a discharge of 700 meter cube per second. The elevations is 300 meters. At downstream river level, the flow at the elevations is 150 meters. Now, the questions is comes it, what could be the invert level of a stilling basins? This is the stilling basins, stilling basin. Basically, this structure we create it just downstream of a dam structures, the spillway structures, so that energy should dissipate. There should be a hydraulic jump formations for the energy dissipations. So, this is what the stilling basins which convert the flow from supercritical to subcriticals, and thus the energy dissipations in quite significant order in terms of turbulent structures and all. So, if you look at this curve, so here it is saying that this Z level, the level at this location is unknown to us. The ceiling bed level elevation, the invert levels of Z, that is unknown to us. If that is the there, and what could be there? So, if you have a 150 meters minus Z, that is the Y2. So, you can compute B1 values. Okay, you can compute the, because you know the discharge. So, you can compute the what could be the B1 value. Substituting that, you have a mass conservation equations, and you can compute it the what will be the Y1 value. So, because you know this B1, and you can compute it what will be the Y1 in terms of Z. And then we are just substituting the relations of the similar way, the upstream flow Proud numbers we can write in terms of the V1 velocities, and we can have a relationship between Y2 minus by Y1, and that is what will be give us a relationship with a flow Proud numbers. That is what we are giving it, and these equations, because these are the functions of Z, but you can see it is not a linear equation. So, you have to do a heat and trials. Okay, there are a lot of tools are nowadays available. You can do a heat and trial methods to find out what could be the Z value. So, in this case just comes out to be 132.04 meters. So, this type of typical examples we can do it for energy dissipations of in downstream of a dam or energy dissipations in a rivers if you know the flow characteristics, assuming it is a steady flow. So, that is the discussions we are doing it for. Now, if you look it, this part I will as a concept wise I will tell it, because this is supposed to discuss in open channel flow, and since we are talking about the river flow, it is just a rectangular channels, we are just have a discussions levels which already we have that. If you are considering a rectangular channels, okay, so which and that is the case, and you have a hydrostatic pressure distributions, and you consider is a uniform velocity distribution. So, we can define the specific energy. This is just a repeating of that. Now, we are just using these functions. As I said it earlier, we have in a flow, we have a 3 cases. One is specific energy, second is the flow depth, Q is the flow discharge per unit width, discharge per unit width. So, basically what we are looking at which locations will have a specific energy is minimum. That is very simple things. We know the E is a functions of Y and the Q. If I consider Q is a constant, if I consider Q is a constant, at what Y depth we should have a E is minimum. So, if you look at this, it is a very easy, because it is a quadratic equations. E is a relationship with a quadratic equations in terms of Y and Q, and Q is considered as a constant here. So, you can have a basic your calculations knowledge is that you can find it dEy by dy equal to 0, either function will be maximum or minimum at that point. That is what you compute it and find out that the yc is comes like this. Same way, if it is to be minimum, then second derivative of E with respect to y should be equal to positive at that. That is what you have equated and find out that is always will be positive. And if you substitute all the follow, that you will find that it happens the E is equal to minimum, it happens only when you have a flow is critical. That is what we did it. Graphically we present in a specific energy curve, we discuss it. This is just a mathematical form to talk that when you draw a specific energy curve with respect to y, you will find a point where you will have a minimum energy, because E and y have a cubical relationship with a for a constant distance. So, because of that you can just have a arrange and just do the differentiations first derivative and second derivative and equate it, you will get it the at the critical flow depth you will have a E equal to E minimum and the flow proud numbers is equal to the 1. That is the same concept what we have derived in specific energy curve, the same things we have given it in terms of mathematical justification. Now, let us discuss about as I said it, we look at the specific energy y and the key. So, now if I consider E is a constant, that means I am considering a channels where their energy dissipations are not happening yet. Okay. The energy dissipations is not that significant. The flow will be varied with variations of y and q. Q is discharge per unit width. That means if same amount of capital Q is coming it as the channels expanding it. So, your Q value at this point this will change it, And if I are assuming there is no energy losses, and we adopt this, the basic concept that if the Q is varying it, what will be the relationship with Y? Whether we can get a maximum discharge, the Q value, the maximum discharge value for a particular specific energy. That is the concept what we are looking at. The same way, now we are looking the same specific energy equations we have written in terms of the Q, the discharge per unit width, that is we also define as a unit discharge. Again we have said that when you have a depth equal to 0, Q equal to 0, okay, no doubt about that. And when you have a Y equal to U, the Q equal to 0, okay. So when you all the energy is now the flow depth, there is no energy is available for the momentums, okay. That means there is no velocity, so there is no flow, okay. That is the conditions we can see it. These 2 points can be obtained in the curve, so we know these values. We just looking at where it will be the maximum or minimum. So we try to look at the first derivative Q with and the Y and the second derivative, and if you compute the second derivative, just same equations, we are just rearranging it and resubstituting it. And if you look at that part, if you look at the second derivative part to be determining and to for flow is rate is maximum or minimum, what we interestingly found it that if I draw the Q values and the Y values, we will get a typical curves like this, typical curve like this, typical curve like this for a constant specific energy. For constant specific energy, you can have a like this. And that is what we have discussed, is that the specific energy will be the E1 when you have the Q equal to 0. So that is the 2 points you will have. We are just looking at from these derivations, we can find out Q will be the maximum when the Y is equal to 2/3 of E1. Okay, that is from simple derivations you can find out, that is what is here. So you can find out, so in this curve with the 2/3 locations you can have this values, and this is what the Q maximum. Beyond that it is not possible. Okay. So that means what is indicating it, that if you are taking a channels and you have the specific energy is constant or the energy dissipations are not happening it, in that case what will happen it, there will be a critical point or the critical flow depth where you have the Q will be the maximum, Q will be the maximum, and Y will have a relationship like this, 2/3 of specific energy. So simple derivations if you do it, same way you can just substitute it, you will get it, the Q max will be a functions of the specific energies. That is what, just substitute the values, we can get it this relationship, which is very easy to do it. So we can draw this curve and remember it, how do the E, and for a constant E, how do Y and the Q, the unit discharge variations are there. That is the relationship what we have got it here. Now let us discuss very interesting concepts, is that we know it very basically that critical flow occurs when you have the gravity force is equal to the inertia forces. That the concept we know it. But how can you know it that there will be a subcritical and supercritical flow in a river flow systems? The most often the river specialty says that you go to the bank of rivers and throw a stones and create a disturbance over the rivers and try to look at the propagations of that disturbance, whether it moves to upstream or the downstream, whether it does it propagate in both the directions. Based on that propagations, we can identify it whether the flow is subcritical or the supercritical. We should discuss now the critical flow concept with respect to the disturbance propagations, or the river flow is happening, there is immediately there is a wave, the huge runoff is coming and it creates a wave as a disturbance. How does that propagate it? Based on that propagations, what is the directions of the propagations? We can find out that whether the flow is subcritical or the supercritical or the critical flow. That the concept we will talk it. As I said it, just throwing a stone in a river, we can find out whether flow is a subcritical and supercritical, how it happens. Let us go for a simple derivations, which more detail you can go through the open channel flow by Hanif Chaudhary book. But let us have the concept is that we can define is a celerity, that is what is called the wave celerity. It is defined as the wave velocity with respect to velocity of medium when which the wave is travelling it. Again I am just repeating that we talk about celerity. Celerity means that wave velocity with respect to the velocity of medium. That we create a wave and we try to find out the wave velocity, the velocity of the medium is a flow where the wave is travelling. That the velocity we call the celerity. Now if you look at these cases, that I have the channel flow and we have created a small disturbance here, small wave. We try to look at what does it happen in this small disturbance what we have created, what it actually happens to that disturbance. If there is a delta y depth, suddenly there is a increasing of the delta y depth and you have the cross section like this. So, that is what the y plus delta y depth. If I have a delta y of depth and you have the y depth here and upstream and this, and you create a disturbance like this, and we talking about the wave celerities, which is the VW. What is the wave velocity with respect to the mediums? The medium is moving with velocity v, and because of this change in the wave, we have a change of the velocity equal to v plus delta v. There is a increase in the velocity. Similar way, there is a increase of flow depth from y to y plus delta y. So, if this is the conditions, this is unsteady flow conditions. This is the unsteady flow conditions. What we can do it? We can consider a moving control volume with VW. Moving a control volume with a VW, the problems becomes a steady problems. It's quite easy now. The problems becomes the steady problems. Neglecting the friction forces, we can use these control volumes for mass conservations and the linear momentum equations to get it what would be the VW value. That's the basic idea. Again I want to repeat it that we consider a disturbance or the wave in a flow where you have a velocity v and u, and because of the disturbance the flow depth has changes from y to y plus delta u, v changes from v to v plus delta v, and let me consider the VW is the wave velocity which is moving on this. To consider these unsteady problems, we consider a moving control volumes with a VW velocity, and that is what again we change the relative velocity components and we have the y depth, y plus delta y depth, and for this control volume we apply mass conservations and linear momentum equations. To know it, what is the relationship between VW with V and Y? That's the basic ideas are that whether we can establish the relationship between VW and Y if I have there. Here again we have considered that the hydrostatic distributions, pressure distributions. Okay. The pressure distribution is hydrostatic pressure distributions. That is what if you look at the force acting on the upstream side and the downstream sides. That is what you can just hydrostatic pressure distributions for y depth and y plus delta y depth. That is what we can compute it, what is the amount of force is acting as it coming as a pressure force onto this thumb. So, net force acting on these directions, neglecting the friction forces, you will get this part. That's what will be equal to same concept, is the time rate change of the momentum flux. So, we find out the relative momentum flux and the mass flux. If you look at that, this is the mass flux, and finding out the change in the velocity at upstream and the downstreams. And that the phases is a momentum flux, we are getting it, and if you are just using this force is equal to momentum flux, you will get these equations. Okay, the simple derivations here, and if I neglecting a very higher order terms, like I am not interested to know it, the multiplications of delta y square or delta v and delta y, because these are higher order terms, because delta y is a small and delta y square will be very, very small. Okay. So, delta will be the very, very small. So, similar way, if you use neglecting the higher order terms, these equations comes out to be only this, with a very simple things. Okay. It looks very complicated here, but if you neglecting these higher order terms, we can come back to these ones. Now, we just use a continuity equations, the mass flux in, mass flux out for these moving control volumes, you can get it. Again, neglecting the higher order terms and combining this is finally we are getting this relationship, the relationship between the v, the velocity, y and the Vw. If I rearrange it, I will get it, the Vw is a v plus minus root gy, and c stands for the celerity. That is what we are looking at with the v value. So, the celerity comes out to be c equal to gy. So, if you try to understand it, that is what we are talking about. So, when you have the flow Proud numbers b by gy or b by c, you can understand it, what it happens to the flow Proud numbers. It is a very simple things what I try to show you. So, if you look at that way, the flow Proud numbers is equal to 1 when you have the wave celerity, the speed of this, the wave is equal to the flow velocity. Then we have the conditions when we call this critical flow. That is the conditions happens the critical flow in definitions of the flow Proud numbers wise. Earlier we discussed it that flow critical numbers is a ratio between inertia forces by gravity forces. Here we are talking about the same concept, is that flow critical happens it when you create a disturbance, and that disturbance speed and the v, the flow velocity, they are equal each others, then you will have a flow Proud number 1. So, in terms of wave celerity, we are defining the flow Proud numbers. Now, very interestingly, if you look at, there will be two part will be there. So, the Vw can have the positive values and the negative value depending upon the V and C value. The case is when you have a flow yield with the subcriticals, V is lesser than the C, you will have both the components, positive as well, V minus C will be the negative components. So, that means if you do any disturbance, it will propagate both upstream as well as the downstreams. Just try to look at how the wave propagations. In case of the subcritical flow, if you look at this Vw, as the V is lesser than the C, so you will have a negative component, you will have a positive components. You will have a upstream directions and also downstream. So that's what the subcritical flow, it happens it. That's the reasons when you throw a stone, you can see the propagations of the wave in the both the directions, then it is a subcritical flow. But in a critical flow, there will no propagation in the upstream directions. So there is no flow in the wave propagations of upstream directions. All what it happens, it will propagate the downstreams. That is a subcritical flow. That will be the wave will be just propagate the downstream on this. So that is the critical flow conditions will happen it when you have this case. But if you look at the supercritical flow, both the case will have the positive, because as B is greater than C, these two roots B plus C and B minus C, they both will be the positives. That means in case of supercritical flow, we will have the wave propagations, both are directing to downstream directions. That means whatever you do any disturbance, it propagates the downstreams. It propagates the downstream. But the flow point of view, what we call it, that when you have the supercritical flow, that means it is upstream controls, because if you do anything, it from the upstream is propagated to the downstreams. So the supercritical flow we call upstream control system. But in case of the subcritical flow, what it happens, if you create any disturbance, it moves both upstream as well the downstreams. That means it can start from the downstream to the upstreams. So that's the reasons it called downstream control. Downstream controls, because these are the informations is necessary when you do the river modeling, whether flow is subcritical or the supercritical. The critical flow, does it happen but it happens very rare conditions. When many of the times what the river flow you consider it subcritical turbulent structures. Please try to remember that the most of the river flows are classified as subcritical and turbulent flow. So there is no laminar flow, and some of the cases, like if there is a sudden hydraulic drops are there, the relief is there, gorge is there, there could be the formations of hydraulic formation of hydraulic jump and the supercritical flow. Those the conditions we can see that it will be the upstream controls. The disturbance what will propagates only in the downstream directions. So anything you control in the upstream, that's what will affect the flow things. That's the way we define it. That's in terms of flow behaviors we can understand it. Is it a subcritical, supercritical or the critical flow with respect to wave celerity. So we defined as wave celerity. With this I used to conclude this lecture today.